well, I guess I should go back and show you what it's called in case you try to find it. Come on, there we go. Ah, don't hit forward or back. Right. The guy that's called 3D graphing site. See this one here? If you click on it, it takes you to here, right? This one, CalcPlot 3D. And there we go. Now, in this box here, you type the function that you're trying to do, the surface you're trying to get your contour plot for. And see this little red guy? If I put my mouse over it, you might even see it say it. It's contour plot. So boom. And then create plot. Now, isn't that cleaner and nicer and easier to see? And I think that's really cool. And you have things you can adjust. Obviously, you can now if I leave that, there you go. If I hit graph, oh, it does that. There. Oh, didn't know it did that. See the things you get when you don't know what you're pressing. Oh, there we're back again, right? So you can have your simple contour plots. These are much easier. Shaz told me that you have to be careful about some of the questions, that the scales, you know, the X's and Y's that are here may not be the right scale for you to judge your contour plots, right? So I don't know, I'll make a change to this just to see what might happen. Is it -5 to 5? I think you mentioned it was a normal scale.
I think that's one of them, yeah.
Yeah, so have a look at the scales, because if you change the scales, right, I guess I may have to go back in and back out just to keep it happy. No, it hasn't changed that. I'm surprised.
That one. It might be other stuff, I don't know.
Right there. Well, if it doesn't change the scale, you can at least play about with it and see if you can make it change the scale. The scale I'm talking about is this -2 to 2 here.
When you create the plot, I saw that you can scroll down. Maybe the scale's there.
Oh, okay. Right. So click on this.
No, Charlotte.
No, I can see. No, but that, even if that doesn't, I mean, if you play about it, you might have the opportunity to do that. But it's still a good program, right? I still like this one better than the other one, right? It's cleaner to use and it's easier to use. So there's a little help for you. Now, let's stop sharing that and start our new section. We are going to look at, God, what's the number? I can't remember anything today. It's going to be 14.2. So, section 14.2. And we're going to look at limits and continuity of multi-variable functions. That's a mouthful. So let's see what that looks like. Well, let's show you what a limit, or remind you again what a limit looks like in the good old 2D world, like Calc 1. If I asked you to find the limit as x tends to 0 of x squared plus 1 over, I don't know, say 2x plus 1. There are a number of techniques that you can use to find the limit. It's almost always, but not exclusively, fractions. But there are a number of ways in which you can find a limit. The first one is what I'll call evaluate. That's simply just plug in 0, and if you get a number, you got your answer. In this case, 0 squared, 0 plus 1, the answer is 1. So that would be one technique. A second technique is called factor and cancel. In a factor and cancel question, so I guess I'll point a lot out. You might get a question something like this. Let's say the limit is x tends to 1 of x squared minus 1 over x minus 1. Now, if you try to put in the value of 1 here, you get that horrible 0 over 0 situation, and not really our friend. Excuse me, I'm just changing something. Darn it if I can find it when I want it. There we go. Right, so back to what I was doing. So in factor and cancel, what you can't plug in 1 because you get 0 over 0, which is called indeterminate form. But if you can, sometimes you can, other times you can't, you can cancel. And you get this, but this you can get the answer to. The third technique is called L'Hopital. I'm not going to show you L'Hopital because we will not be able to use that technique in multi-dimensional functions, right? Multivariable functions. So it exists, but not for us. And then you have a guy called the conjugate method. Can anybody remember what a conjugate method looks like? What it's got in it that would
Square root.
Yeah, I kind of wrote it before us, but yes, you're right. Try to figure out how to get one that works. Yeah, that would work. If you plug 1 into here, do you know you get 0 over 0, right? Indeterminate form, you're stuck. You wouldn't use L'Hopital on that, because if you did, wouldn't you just get square roots with more square roots? Typically, at least, I would avoid L'Hopital. In the conjugate method, you multiply by the same square root guy, but with a plus 1. What happens then is that the top things multiply together, but some really cool happens. The square root times the square root gets you that. Take away 1 squared gets you that. And the other 2 terms cancel out. You know, like there's a square root of this, but later on there's a take away the same square root. So that's all you get. And on the bottom, you get this guy. Now, right now, it doesn't look like you're getting much benefit out of it, but you keep going and you do. If you pull out a common factor of 2 in this question, can you see what you're left with is a 2 over this fella, which is what, 2 over 2, which is 1. So it works. I know it's speeded by that, but essentially conjugate method.
Could you bring your
multiply the guy by its conjugate. That's what we call these. That's where it gets its name from. So it's the same square root, but a plus instead of a minus. And 5 or so lines later, the whole thing works. So that's kind of the history of how we would typically find limits in the old days, when it was a simple function of x, a 2-dimensional function, essentially, because there's x and there's y. So how do we do it when we have limits of functions where there is more than just x? Now, let's show you. This is question 1 from 14.2. It's going to be the limit as xy tends to the origin. So it's not x tending to 0, it's not y tending to 0, but it's both of them tending to 0. So this would essentially be the limit of the function as x comes towards the origin. And it's typically going to be fractions because they tend to cause the trouble. And we are going to be asked, does this limit exist? And if it does exist, find it. Or does it not exist, right? So find if it exists, get the answer, and find out if it doesn't. You know, some limits do not exist because the answer is infinite, right? It's like 1/0, right? And we're going to just call them DNAs, right? Does not exist. And that's the answer you'd put in your homework. But none of the techniques that I've showed you work for this question. You could try and factor that, but would you agree it ain't happening, right? So the factor method's out. There's no square roots, forget it. L'Hopital hasn't got a chance, it never did. So I never even mentioned it in the intro. Factoring cancels out. If I plug in 0, don't I get 0 on the top, 0 on the bottom? So there is a new method that is now introduced only for limits of multivariate functions. And you do this, you find the limit along both axes. Axes, yes. So this new technique of finding the limit along both axes, what on earth does that mean? Well, let me show you. I am going to find the limit of this guy. And I'm going to find its limit along the x-axis. So if you're traveling along the x-axis, isn't your y value 0? So what you essentially do is you take this limit and you reduce it to x comma 0 going to 0, 0. Well, let's see what happens when you do that. You're going to have x to the 4, take away 6 lots of nothing. You're going to have x squared plus 3 lots of nothing. Do you notice that the y's have turned into zeros? Now, you can pretend, algebraically it's not pretending, but you could say that it's the same thing as that, isn't it? Now, what can we do to simplify this? Can't we just cancel some x squareds? Which means that we now have the limit as x tends to 0 of x squared, and we know that's 0. And you're about to say, great, that limit exists and it's 0. Hold your horses. You have to check both axes. So I'm now going to do the same limit, but along the y-axis. And if I get a different answer, it means the limit doesn't exist. Because shouldn't the limit be the same number all the time? It can't be, it's 0 on Monday, but 2 on a Tuesday, right? That doesn't work, right? It can't be. So let's do that, fella. And this time, I'm going to do it along the other axis. So let's do it along the y-axis. Now, if you're doing along the y-axis, doesn't that make x 0? Great. Now, if you have x 0, you get nothing take away 6y squared and nothing plus 3y squared. And that now can be written as just a y tending to 0 of negative 6y squared over 3y squared. Oh, wait a minute. Don't the y squares cancel? And isn't the answer the number negative 2? Conclusion. You're finding the limit as you travel along the x-axis and it goes to 0. But then you try and find the limit as you travel along the y-axis and it ends up being a totally different number. Conclusion, the limit does not exist. Can you imagine a piecewise function that was broke? you know, a jump discontinuity. You come in from one side, it's 3, you come in from the other side, it's -2. Doesn't that essentially mean does not exist as an overall limit? I don't know if that's a good analogy, but it's a kind of analogy, right? So you travel along the two axes, the X and the Y axis in this case. We're not going to do it, but can you imagine you could continue it to X, Y, Z becomes 0, 0, 0. You could travel along the X, along the Y, and finally along the Z. And if you get 3 different, well, if you get anything that's different from anything else, the limit doesn't exist. If all of them equal each other, then it's a good indication that you have a limit that does exist. Now, the next question is the limit as xy tends to 0, 0. They kind of like this as a choice. The technique of traveling along the X and traveling along the Y axis don't work. You just end up with zeros, overs, and zeros, right? And that's indeterminate form, so you don't know anything. Do you recognize that this one is an ugly version of one of the techniques I mentioned at the start of today? There's a big clue there.
Conjugate method?
Correct. So this one is a conjugate method. So that technique, right, the conjugate method technique does transfer into this world. Now, let's see how it transfers, and hopefully it will transfer in a nice way. So you take the same square root, but with an add 7. And do you notice that the conjugate method doesn't care if the square root's on the top or the bottom, right? It has no effect. Now, that's going to be the limit as xy tends to the origin. On the top, I'm going to have x squared plus y squared times this large, quite ugly square root. And on the bottom, if you multiply this guy by this guy, right? This guy times this guy, you get x squared plus y squared plus 49. Take away 7 squared. Are you happy with me doing it the quick way rather than foiling all out and proving to you that's what you eventually get? Now, it takes a couple of lines, but things are going to happen that are kind of pretty. The 49's cancelled, and you see you're just left with that. Can you see why that's pretty and nice? Cancels. So the original limit, which was really something we couldn't solve, has now been transformed using the conjugate method into this fella. But this guy, can't you just get him by plugging in 0, 0, right? The evaluate method. And so we'll do that. Nothing squared plus nothing squared plus 49 plus 7. 7 plus 7, 14. So this limit exists and it is 14. So one brand new method, right? Evaluate along the x-axis, evaluate the limit along the y-axis, right? That was the first one we did. That's a new method. We've never seen that before. And then this method, the conjugate method, which is really one that we've done, kind of extended a little bit, but not that much, right? It's pretty much the same method. And we're good. Any questions? I think this is going okay, but I can't see a lot of faces, so I'm only going by the ones I can see. Are we okay here? Right, let's move on. See if I can find a different technique for the next one. I'm trying to find a factor one. You never know. Ah, got one. Find it. Let's find the limit as xy tends to or 0, 0. And we have x to the 6, take away y to the 6 over x cubed plus y cubed. And although I could do this question as a limit along the x and a limit along the y, I don't think that really helps. It might not be obvious to you, but that top thing factors. X to the 6 take away y to the 6 factors is a difference of 2 squares, just like x squared minus y squared is. It's just that the things that are inside are a little bit different. Are you comfortable with that being the factor of the top? Can you see where the bits that I've got are coming from? Do you also see some cancelling? And yes, it has a limit, and isn't the limit 0? So we've seen a conjugate, we've seen a factor and cancel, we've seen that brand new one, travel along the x, travel along the y. So I'm now going to show you a limit question where you can just do the evaluate, right? So they're probably the simplest of them all. Well, there's one right above, so I'll use that one. Let's find the limit as this guy travels to 1, 1. So the answer is going to be 8 take away 1 times 1, 1 squared plus 5 times 1 squared. 8 take away 1 is 7, 1 plus 5 is 6. The answer is that the limit is 5, sorry, the limit is 7 sixths. Now, if you don't know what kind of situation you've got, wouldn't the first strategy be just to plug it in and see if you get an answer like this? And only when you get that 0 over 0 indeterminate form do you then have to think about other techniques, right? Maybe limit along the x, limit along the y, and perhaps factor and cancel. I'm pretty sure if I saw a square root, I'd just be thinking conjugate right off the bat. But, you know, I guess you could do a square root where you could just evaluate the answer, couldn't you? You could do a question where the numbers just work. You don't need to worry about it. But if I saw a square root, I'd be thinking about that. Are we good so far? Right. Now, when a function has a limit at a particular point that might be causing trouble, like at 0, 0 or 1, 1, wherever it might be, if it has a limit, the net effect is that these are surfaces, right? Imagine curved surfaces. It means that you've got a continuous curved surface, right? There isn't any weird things going. If the limit doesn't exist, doesn't that very often mean that there is a problem with your surface? And we use these terms problem. We use a word called continuity and discontinuity. Isn't continuity nice? It means it's nice and smooth. And discontinuous is bad news, vertical asymptotes, holes in the curve, piecewise functions. It's broke, right? There's something not right about it, at least in part of it, right? So we are going to now look at, well, I just get kicked out of WebAssign. Brilliant.
So are we finding the limits of a plane in 3D? Is that?
Yeah, you're finding the Z coordinate of a plane, of a surface in 3D. The limit is what the Z value would be at x 0, 0, for instance, right? If it was limit as x tends to 1, 1, you're finding the Z coordinate at 1, 1. right? You're finding what the height of the surface would be at that point. You don't want, I'm doing it with hands because there's the only way I can do it. Can you imagine in 3D that you could have what would be like a vertical asymptote? Where as you get nearer to one point, it's like a very thin spout, maybe shooting up the way, or very thin spout shooting down the way. That would be a bad thing, right? That would be a discontinuity. How would you know that? Well, when you try to find the limit at that point, it doesn't exist. And one of the reasons it might not exist is because it's infinitely large. But there are other weirder discontinuities in surfaces. Can you imagine a surface? I'll try and draw it. Can you imagine a surface that was broken like this? Like somebody took a nice surface, cut it with the scissors, and bent one side up and one side down. Along that pen direction, wouldn't there be a whole load of places that you couldn't evaluate the function? Because on one side it would be 10 and the other side it could be -10. These are features of discontinuity. The one I was trying to maybe give you an example of is, can you imagine that might be what a 3D version of a vertical asymptote could look like? Can you imagine at this point it just keeps shooting upwards and upwards, right? If you were looking at the limit there, wouldn't the limit probably be plus infinity? So the 3D discontinuities are kind of in some ways like two-dimensional ones. Isn't this a bit like a jump discontinuity and this is like a vertical asymptote one? The only thing is that 3D has lots more other weirder shapes than even that. You can have functions where it's basically the surface has been given a twist. And if you come in one side, it's a different number than if you look at it from another side, another direction. So let's look at discontinuity. And continuity. And if you hold on for a second, I'm going to have to go back in and find some questions. What the heck's that doing there? Go away. Ah, found one. God, WebAssign's been a pain today. I'm trying to find my first discontinuity. Okay. This is question 5. Here is a function. And we're being asked, where is this function discontinuous? What relationship would cause bad things to happen? You see it's happening here, isn't it? Now, it's not just, you know, in the old world, wouldn't it be x equals 4 as a discontinuity, right? There'd be one place, which would be a bad place. And here it's a little bit trickier than that. Isn't this going to be a bad place anytime x is equal to y? Would you agree if the x coordinate is equal to the y coordinate, won't the z coordinate have a problem? Right. So there is your discontinuity. Places where bad things happen are typically, and not exclusively, but are typically not single points anymore, right? Now, if you wanted to do it a little bit more formally, you could do it like that. Now, this is all the places where the function is discontinuous. If I wanted to know where all the places where the function was okay, wouldn't the answer just be the opposite of that? So, you know, if you know where something's continuous, don't you also know where it's not continuous, right? Where it's discontinuous. They're like left and right hands, right? How about this function? Where would this function have problems?
Where x squared minus y squared equaled 0.
Yeah. Or x squared equals y squared, equally correct. What Catherine said was bang on. How about this one? And I want to know where it's discontinuous. So they're calling it D, which is nice because I don't have to write the whole thing. Where would this function have problems?
Could we do what we did in the last one where we just said 5 minus x squared minus y squared cannot equal 0?
Well, that would be it for continuous. To be discontinuous, you say 0, right? And that is correct. The book does this, or WebAssign does this, which is the same information. It just looks prettier. So if you wanted to know where it is discontinuous, that's your answer. If you want to know where it is continuous, that's your answer. Do you see that it's the same information, right? When are you good? When are you bad, right? If I know when you're good, I can tell when you're bad, right? If you say, I'm good all the time, except right at the weekends, well, you're good Monday to Friday, you're bad Saturday and Sunday, right? Whatever it might be. Discontinuous is bad, in my opinion. Continuous is good. Because functions that are continuous, you can do lots of cool things with them. Functions that have discontinuities are a pain in the butt because you really can't do much with them. Not at the places where they're discontinuous, at least. Any questions about continuity or discontinuity? Okay, let's try some unusual functions. This one is like question 10. Oh God, the time, got to be quick. Now be careful. Sometimes they ask you when is it discontinuous, and sometimes, like right now, they're going to ask you when it is continuous. So they're asking when it's good. So what's the problem with a log function? Well, things inside log functions, don't they have to be greater than 0 or the thing doesn't exist? Are they allowed to be equal to 0? No. So if I wanted to say, where is this continuous? Where is this good? You would say that. And that would be correct. But to keep WebAssign happy, you would write that. Now, that question was asking for this function, where does the function exist, right? Where's the function usable, right? Continuous. They could have said, where is it discontinuous? Do you see what I'm getting at when I say if you know one, you know the other? You can either be continuous or discontinuous, right? You have to be one or the other, right? So if I know half the picture, I can really figure out what the other half is. So in this case, in this question, that was the one that we're asking for. But who knows, maybe in the next question, they ask you for this one, right? So just make sure you're reading which of the two you're being asked to write down. That's okay. That's okay. That's okay, done that. Yeah, done one like that. Done this. Okay, I got a few seconds. Yeah, let's do that. Just bear with me for a few more minutes. I'm trying to find. Gotcha. And let's go into dashboard. I'm going to draw some sketches of some of these functions and just figure out if we can visualize what the problem is. It's kind of nice to see them because all we've been doing is finding out the answer. We haven't really done anything particularly visual. So okay, let's move this over and I'll put in one of those functions. Can I do a full screen on this? It's a bit better. Okay, let's do that one, e to the 1 over x minus y, right? So e to the power of 1 divided by a little bracket x, take away. I know you hear something like now. Remember that one had a problem at y equals x, right? So the whole sequence of points. If I turn this fella side on, can you see the problem? Can you see how the curve goes up this way and then it comes down that way? If I orientate it a little bit different. There. I know that looks like a motorway, but if you look at it vertically above, it's just a straight line y equals x. A whole sequence of points where the function has problems. If you come in from one side, you see it shoots off upwards, essentially to infinity, and it shoots off downwards. Wouldn't that be the equivalent of 141 vertical asymptotes that do that? You know, one side goes up and the other goes down. Now, if I take that same function, I'm going to tweak it a little bit, and hopefully I can do it. It's kind of tiny. But if you go that guy squared, so it's basically got the same problem, right? X equals y is a bad problem. But do you notice that what's happened now is that the shape of the problem has become more like a vertical asymptote? Both sides zoom off to infinity, but it is still a problem, isn't it? So that's one example of a discontinuity. Let's see if I can find one of the earlier ones that we did. Right. The first one we did, so it's going to be a new function now, was we found the limit of, do a bracket, x to the 4, take a, subtract 6 y squared. Then we'll do a divide. Not there I want, outside the brackets. Now I'll do a divide. And on the bottom, we had an x squared. And a plus 3y squared. In this question, we found out that the limit is you tend to the origin had a problem, right? So click out. Let's see what is happening here. I'm sure I can see this one. Right, if I come in from this side, it looks like it's got a 0 value. Not so obvious here because there's so much blue in the way. But I think if I come in from the y value, it's homing in on a different number. Maybe if I rotate it a little bit, can I see it? Nah.